Bit Simply 5. Learn, loop, evolve.
We experience a second as a rigid, unyielding tick of a clock. But that steady rhythm is an illusion. How fast your watch ticks is entirely dictated by where you happen to be standing in the universe. To understand why, we have to look at Albert Einstein's theory of general relativity. He showed that space and time are not separate things. They are woven together into a single four-dimensional structure called spacetime. If you place a massive planet onto that structure, it causes the grid to curve downward. What we feel as gravity isn't an invisible tether pulling us to the ground. It is the physical geometry of that curve. And this geometry creates a paradox. The speed of light is a constant absolute speed limit. If a beam of light has to travel through a stretched, curved region of space, it must cover a longer path than a beam traveling through flat space. To balance the math and keep the speed of light constant, time itself has to slow down. So, the heavier the object you stand on, the deeper the curve, and the slower your clock ticks. Gravity actively dictates the physical rhythm of your life. Our Earth is relatively light, creating only a minor dimple in spacetime. But look at Jupiter. It has 318 times more mass than Earth, meaning it creates a vastly deeper, steeper gravitational well. Because you are deeper in that well, a physical second spent floating in Jupiter's atmosphere lasts tangibly longer than a second spent on Earth. Mass alone stretches time, but rotating mass creates a specialized effect known as the lengthens effect, or frame dragging. When a massive planet spins, it drags the geometry of space and time along with it. It acts like a spoon stirring a thick jar of honey, creating a cosmic whirlpool. If you try to send a light signal through that rotating space, the coordinate system itself is moving. The signal is pulled off course, forcing it to traverse an even longer distance and severely compounding the time dilation effect. We live inside Earth's specific gravitational time zone. To test the extreme limits of Einstein's math, we need precision instruments capable of mapping these invisible distortions across the entire globe. We already manage this distortion every day. The GPS satellites we rely on orbit 20,000 kilometers above the surface. Up there, gravity is weaker, meaning their clocks tick about 45 microseconds faster every single day compared to clocks on the ground. If engineers did not continuously correct the software to compensate for that faster time, GPS coordinates would drift by 10 kilometers every 24 hours. The system would be useless. To map time dilation with greater precision, the European Space Agency is developing an experimental vanguard. The first stage is the ISOC Pathfinder, a payload for the outside of the International Space Station. This diagram illustrates how the mission works. It uses an ultra-stable hydrogen maser and pulsed laser links to synchronize cutting-edge optical clocks located on entirely opposite sides of the planet. Here we can see the primary objective. When two ground clocks are at an equal position relative to the Sun, they experience a constant gravitational potential. But as this next schematic shows, Earth's rotation shifts these clocks into slightly unequal positions. One clock is pulled deeper into the Sun's gravitational field. This creates tiny differences in tick rates, generating differential data needed to test the Einstein equivalence principle. ISOC Pathfinder is the crucial first step in transforming the space station from an isolated laboratory into a planetary-scale scientific instrument. The next phase of the campaign is the GEO-OTT mission, which breaks past the low-orbit limits of the space station by placing a time transfer satellite much higher in geosynchronous orbit. This extreme altitude allows for common view time transfer. Instead of waiting for a satellite to fly over one clock and then the other, the satellite can see multiple ground clocks simultaneously, enabling near-instantaneous comparisons. This technical schematic details the payload for that mission. The critical components are inside Panel B, fiber optic frequency combs. These modules act like gears, converting optical frequencies down to measurable microwave signals, maintaining absolute phase-coherent precision. The engineering hurdles here are immense. The satellite has to punch delicate laser pulses through 30 kilometers of chaotic atmospheric turbulence while perfectly compensating for high-speed Doppler shifts. Overcoming those variables yields an incredible reward, a time transfer instability floor below 10 to the negative 18th power. That is orders of magnitude more precise than anything currently possible. GeoOTT will upgrade our orbital infrastructure, effectively turning standard satellites into an ultra-precise cosmic metronome. This global network of optical clocks functions as a planetary-scale sensory organ, detecting physical phenomena that remain invisible to conventional instruments. One of the primary targets for this sensory network is the hunt for topological dark matter. If a topological defect of dark matter were to sweep across our planet, it would physically alter the local laws of physics for a fraction of a second. This network would detect that event as a measurable imprint or phase shift, rippling across specific clocks as the wave passes over them. This incredible precision also unlocks an entirely new field called clock-based geodesy. Because water has mass, moving water changes the local gravitational field. By measuring the microscopic changes in how fast these ground clocks tick, scientists can map the Earth's gravitational potential in high resolution. They can track the physical movement of ocean currents or the depletion of underground water tables just by watching time fluctuate. This ground-up temporal data perfectly complements existing space missions, like GRACE, combining to build a highly detailed model of our living planet. The culmination of this entire staged campaign is the redefinition of the International Atomic Timescale, sinking global timepieces down to the 100 femtosecond level. By tracking the microscopic stretch and twist of the space-time fabric across the globe, this orbital network provides a definitive map of how gravity and mass dictate the physical rhythm of our world.